morning, good afternoon, good evening, and welcome to another episode.
Working on OpenShift
and sometimes
we haven't.
This is so awesome.
Are an open culture that
it's actually
in
a big piece of the component for your GitOps work.
Everybody has something that they get to
On top of the Red Hat portfolio.
Whoa. You did the old video, Jonny. Also, what did it do to our view? There we go.
That view is bizarre.
That is so weird.
Yeah. So yesterday when I was setting it up, I was like, I was like, I'm going to figure out what each one of these videos does. And so I sat there and I watched each one. I was like, oh, this is kind of cool. It's a little throwback. So I committed to doing it today. So that's why we did it.
I was surprised. Thank you for that. Well, it's good. Throwback for the throwback. Because our guest today is a bit of a throwback, but we'll get to that in a second. Hi, Dave. Hi, hello, GitOpsians. As I think a lot of regular viewers know, we were supposed to have this episode last week. So preemptively, I thank you all for joining a week off of our usual cadence. I'm sure you were all confused. Dave, thank you for rescheduling. There was an unfortunate a death in my family that caused me to need to be out of town. My very loving and wonderful grandfather died at 95. And so I needed to be away to attend his funeral and spend some additional time with my loved ones. So heartbroken, sad, but also I got to see all of my family, which was really, really good. So I know he would love that. So again, thank you for the flexibility, everybody. Sorry about that. Speaking of episode cancellations, I have one more announcement before we start getting to the good announcements. I am having surgery in 2 weeks. So there will not be an episode in 2 weeks. And there will not be an episode again until July due to my period of recovery. That could change. I could recover faster than anticipated and be back at work sooner. You're just going to have to take it week by week during that period of time. For those people who watch the stream a lot, you guys know I do HEMA, which is sword fighting. Yes, it's really cool. Unfortunately, my shoulder likes to dislocate sometimes, daily, all the time. So we're switching weapons to rapier, actually, from longsword. So if anybody has heard me talk about that, notice the swords in the background, notice the sword book behind my head, all of these other little things and references to it. Don't worry, it's sword fighting continues. You'll still get to hear stories, just changing from longsword and left-handed to rapier and right-handed, which should be fun. I think. I don't know how to be right-handed. I hear
it's gonna work.
I hear, yeah, it's gonna work.
Yeah, very totally Princess Bride of you there.
Very Princess Bride. I am not left-handed. Well, yeah, exactly. Except it's the reverse, but same moment. That's what everybody has said. Everybody says, "Hey, you get to have your Princess Bride moment." So that's pretty fun. So I will miss my professional opportunity to be inquisitive. Or stupid, as I like to sometimes say. I will miss the stream. I will miss the viewers. We'll have great content for you when we get back sometime later this summer. But yeah, so that's the two sad announcements. I was gone, and now I'm about to be gone again for even longer. And I hope to see you all on the other side of my recovery, still with us and still watching us be professional nerds.
Yes.
That said, we have some good announcements, right? I think we talked about this already. Boston is next week. Red Hat Summit is in Boston next week. I'm just jumping straight to the city. Who cares why?
You'll figure it out.
I'll figure it out. Yeah, Jonny and I will both be there, not presenting together, presenting with partners. I think you've got Deloitte. I've got Dynatrace.
Yeah.
We had a moment for a second where we were wondering if we were doing the same presentation secretly when it was that similar situation. And when we do eventually get back, we will talk about how Summit was and some of the highlights from it. It'll just be on a really major delay. So sorry about that as well. I don't recognize this viewer. My defense will be better switching your sword side once you get the hang of it. I think you're correct. So I've been on shoulder rest since last summer on my left shoulder, and I've been learning right-handed side sword and rapier. Side sword is the historical precursor to rapier. I don't have them handy to show you, although I do own these swords. But there's some things. And what I have noticed is my understanding of the angles is now adapting. So when you're left-handed, the angles and the mechanics, the geometry of fencing is one way. And when you're right-handed, it's another way. And this is why a lot of left-handed people have an advantage against right-handed people, but a disadvantage against other left-handed people by having to like go back and forth between the body mechanics of left and right-handed. I am noticing things are that my adaptability to angles is increasing, which means my defense is increasing. So I believe you're completely correct. I hope it continues to get better. I'm actually excited, as much as I'm sad about not doing longsword anymore in a competitor capacity. I'm switching to a coaching capacity. I'm really excited about that. And I'm really excited to compete in rapier and actually know what I'm doing, because I totally competed in rapier a few weeks ago, but I had never fought with a rapier before. And I used it like it was a side sword. And people are like, why are you cutting? I'm like, because I don't know how this is a stab. I'm used to the cutty weapon. They're not the same thing. Anyway, Jonny, do we have other announcements?
I mean, the big one's just Summit, right? And then, yeah, that's it for now. I think like there's some other stuff going on behind the scenes, but
yeah, we'll be late with some of the like OpenShift release versions and all these other things. We'll catch up on them when we're back. So let's go ahead and actually finally transition. Yes, down to our guest Dave. Dave and I met when he used to actually work at Red Hat, and I'll let him finish his own introductions.
Yeah, thank you, Hilliary. I really appreciate the opportunity to join y'all. Yeah, I used to work for Red Hat for about a decade, from 2012 to 2022. And now I run developer relations for Ampere Computing. So Ampere Computing, for those who are unaware, we make CPUs. They're ARM64 CPUs built for the cloud. So lots of cores, high performance cores, lots of cache per core, and low power, which is really, really important in cloud use cases, and single threaded cores. So you get predictable performance. You don't have any, noisy neighbor issues. That's what we do. And I'm here to talk to you all about using Argo to get your stuff running on Ampere instances more easily, right? More or less.
Nice.
And so I'm going to start with like the very like base level. Sometimes I'm really smart and sometimes I'm really not. So I am so used to OpenShift, where all of the node management and everything is done with the machine API. And I know that does not exist in vanilla Kubernetes because I've seen it. And I know that I'm very, very spoiled by machine sets and machine config pools and all those the machine API that we add to OpenShift. So kind of the stupid question, I guess, and that maybe I'm preempting your explanations, is for this use case you're discussing, are you basically using Argo rollouts to replace the machine API?
No, actually no. So yes, the machine API and every single cloud service provider that has their own hosted Kubernetes service, they all have their own particular way of adding specific node pools for different architectures, which is very annoying. And so, no, the starting point, if you want to use ARM64 instances, ARM64 is the architecture that powers Ampere. If you want to use ARM64 instances, you first need to create a node pool and add that to your Kubernetes cluster. So what those are called, whether they're node pools or what did you say, machine sets or node sets?
Yeah, we call them machine sets.
Yeah, different. Like I said, different Kubernetes distributions and different hosted Kubernetes instances call them different things, which is very annoying. But the first step is you create your ARM64 machine set, you add it to your existing cluster, and now you have the ability to use kind of workload placement rules to get stuff running on those nodes.
So, and this is just my ignorance to the whole thing. So, like, if I order an EC2 that's got an ARM processor out of like AWS, right? Is that by default going to be like, is Ampere like something I would have to select, or is that like the default ARM?
Well, so thank you very much. I appreciate the segue.
My bad.
So ARM64 is an architecture. There are multiple people who are making ARM64 CPUs for the cloud. EC2 makes their own. AWS makes their own. It's called Graviton. So if you get a Graviton instance, then you're getting an ARM64 instance from, AWS's silicon. Ampere CPUs are powering some of the ARM instances on Azure and Google Cloud. Not all, and I can go into that if you're interested. We are also the ARM CPU provider for OCI. And pretty much if you get ARM instances from any kind of hosting company like Equinix, Scaleway, Hetzner in Europe, what you're getting is an Ampere instance underneath. So Ampere CPUs are underlying most of those smaller cloud providers because they don't have the resources to build their own silicon, basically.
Okay, gotcha. Yeah, I was curious because I built a bunch of like ARM instances. I recognize the Ampere name, so I didn't know if I was just making the association or if that was actually there. That's cool. Good to know.
Yeah, no, Ampere instances were underlying the first version of using Red Hat code names, ROSA, Red Hat OpenShift on Azure.
Wait,
but Arrow
ROSA is Red Hat OpenShift on AWS. Arrow is Azure Red Hat OpenShift.
Oh, I got them mixed up. Excuse me.
It's easy.
Okay, it's been only a couple of years since you were here, or whatever.
Yeah.
Yeah. So I have seen Ampere in the context of Arrow, right? Being an Arrow team lead, it's something that we see, although not something that we dictate or mandate. Obviously, customers get to do what they want. That's the beauty of it. I know very little about ARM versus x86. I'm not going to lie. Mm-hmm. I don't know how much you wanted to get into this today versus some of the other, like actually talking about Argo and GitOps and, the things we talk about the most here. But I feel like I started off in hardware and then I moved away from it so quickly that I'm just like, I don't remember. I don't actually know I know high level. I get it. Actual different defining differences, I think, is where I would not be able to articulate.
I can give you the high level defining differences, but I am not a hardware person, right? So just to be very clear, I'm a software person. But okay, so the biggest difference between x86 and ARM64 is that x86 is a CISC architecture, complex instruction set computers. ARM64 is RISC, reduced instruction set computers. So ARM64 instructions at the machine code level tend to be smaller and take fewer cycles to process through the processor pipeline. Practically speaking, from a software perspective, there's almost no difference, right? In terms of if you're writing C code, the C code will compile to it'll compile to x86 or ARM64 binary code based on what architecture you're compiling it on or whether you're cross-compiling. But it's going to run in roughly the same time, roughly the same way. The behavior is going to be roughly the same. And for most programming languages, in fact, if you're running an interpreted programming language or something that has an intermediate bytecode like Java or C#, once the underlying runtime is available on the architecture, which they all are, you don't see very much visible difference at a kind of an application developer perspective. That underlying architecture does have some impact, particularly around code that uses accelerators, right? So if you have code that uses scalable vector extensions, or I'm not even sure what the feature names are on x86, but there is an equivalent to that on ARM64, which is called Neon. So you do have the SIMD, single input multiple data instructions that can do things like vector multiplication and matrix multiplication, things that are very important for machine learning and AI workloads, right?
Right.
So a lot of those accelerators are available on x86 processors and have been for a very long time. So the software projects have implemented the accelerated versions of algorithms like that long time ago, and they've been debugged and they're well embedded in a lot of these projects. ARM64 has been around for a little bit less time. And so there aren't necessarily the implementations in the vector accelerators for the ARM64 equivalent. So that's something, for example, for let me take an example. A couple of years ago, we implemented or helped implement some Neon accelerated versions of video codecs for an Ampere customer. So like you get kind of 100% speed up on certain algorithms that can benefit from things like that. So, I mean, I don't know if I answered the question. Basically, anything that works on x86 will work on ARM64. It's a different binary format, so you gotta compile your code for that target architecture.
Yeah, no, I think you answered it really well. And I was just thinking like when ARM really became like a mainstream topic, right? It was right around Raspberry Pi, and so you had like the Pi 3s and then Pi 4s, and I think Pi 4 is the first one to go like the 64-bit, and so then like yeah, that's like so when you're saying all this stuff, I'm like, oh yeah, that makes sense. Because I'm just in my mind remembering the timeline of when the Pi phenomenon was happening.
So it's there have been ARM servers for longer than that. I remember you just talked about our Red Hat Summit. I remember seeing John Masters cycling a bike to power an ARM server in Red Hat Summit in the Heinz in 2012, right? So there have been ARM servers since, over a decade.
Yeah.
But really there was a gap between the software availability on ARM64 and x86, and that gap really got bridged really quickly with the coincidence of, three different kind of phenomena. One was Raspberry Pis, one was the Apple moving to the ARM architecture for laptops. So you started to see a lot of developer laptops running ARM, and then you mentioned it already. The ARM instances in various cloud vendors became a really compelling, price performance argument for running your software in ARM. So those three things took the small, medium, and large kind of size and really superpowered adoption of ARM64. I'd say about 6-7 years ago, which coincides with when Ampere was founded.
Nice.
Yeah, and that's about what I remember really hearing about. When around that time, I was working in IoT, and we had a lot of ARM chips there. We had some x86 architecture IoT servers. We had some ARM. We had Raspberry Pis. We had something else, Systech. We had, and then a lot of the actual.
You can say whatever you want. I'm not going to recognize the names.
Somebody would be like, "Lady, what is that? That's not a thing." I don't know, guys. Rhymes with. And then a lot of the actual. IoT devices themselves, the smart metering, the receivers, etc., were ARM. But the application on these things, right, is small bytes very quickly, and that's not what we're seeing in the cloud. So that's kind of the fascination for me with where this is. Like you said, the developer laptop area, and now the cloud instances, is it's not necessarily small bytes very quickly anymore.
Exactly right. But that's the origin story of ARM, is right. It was small power, small compute instructions, low power usage, and it was for small compute footprints. What we've seen is that the benefits that ARM had for small compute footprints scale really well to when you're like, I didn't talk about Ampere's core counts. We have products that go from the low end is 32 cores that are all 32, 3 gigahertz or 2.8 gigahertz cores, all the way up to 192 cores running at 3.6 gigahertz. So those are high performance cores, and there are lots of them on the die. What that gives you is it gives you the ability to have, lots and lots of compute in a relatively small volume, which is great for cloud vendors. It's great for data centers, where power and space are really the two biggest constraints.
I think they ran cooler as well. So what we used to do is we used to actually monitor the actual temperature of the IoT server so that we would understand their life expectancy, right? You have these, I don't know if people know this, but when you have like racks of servers, you need to know a bunch of different health metrics about the hardware, so that when it's coming up on like it can help you to forecast and predictively know when you need to replace it, right? If your CPU is constantly keeping your hardware's literal temperature too high, you're going to start melting chips. Certain personal laptop brands that I won't say, but have had to repair before, are very good at running very hot and melting their chips after about a year and a half. I'm not going to say it's planned obsolescence, but I'm not going to say it's not. Anyway, and so if you've ever had your power input stop working on your laptop and you need to replace that, or a USB port go down, or even just needing to replace the fan or re-add, the heatsink material, sometimes with certain brands, it's good to open them up and proactively add additional heatsink material because they tend to not add enough. Like I said, I started in hardware, guys. Nerd moment. So... I remember from the data collection, because of course I did this over a period of years, that the ARM, for the same amount of data throughput, same amount of like runtime hours, our ARM systems were consistently cooler temperatures.
And that holds true in the server chips as well, right? It's like we have lower TDP, and I don't even know what TDP stands for, but that we use less power per socket, which means we run cooler, which means you can air cool rather than water cool in many cases. Sometimes even passive cooling solutions where there's like no fans, you've just got kind of natural airflow, is enough to cool down a server class CPU, which is really impressive. But the biggest argument why people are using these CPUs for the cloud is because we give the cloud service providers so many cores per socket, they can rent them to you cheaper. And so typically on most CSPs, the ARM instances, whatever hardware is underneath them is going to be the cheapest instance available at that capacity or at that performance profile. And certainly that's the case with Ampere instances on, for example, OCI.
Yeah, when I first started looking at HyperShift, which is like hosted control plane, so like if you're familiar with AKS, which you are, right? It's very similar to that, where the control plane's hosted by, in my case, it's my team that's hosting the control plane, and then the compute's kind of like levied out to our teammates.
Right.
And like we were looking at ARM CPUs for the hosting cluster because, like, by and large, there's like a 30% difference in cost, right? Just like total cost of ownership of power, power space cooling, EC2 instances and all that. So it was like, it's pretty significant. And then the fact that you still get, parity level performance with an x86. I mean, there's obviously some things that I say obviously because I don't. It's funny I say obviously I don't know what the things are,
Right.
but there are some things that that don't match up. But we can still run x86 compute workloads, but then have our ARM-based hosting server. And it's pretty interesting how all that stuff works and how far it's come from like I was saying earlier. Raspberry Pi was my first, I think, real insight into the ARM architecture. So it's cool.
No, it's been awesome. And like inside Ampere, I say, the big questions that we have to answer for a developer program are: one, why would I use your stuff? And then two, how do I use your stuff? Once I'm convinced that it's worth it, how, which would bring us nicely into what how Argo CD and Argo Rollouts fits into this whole thing.
We've arrived. We did it.
Yeah. But it's okay. So the biggest issue for people is they're like, well, this is fine. I like the idea of running, the cheaper instances, but is it going to be work? Am I going to have to recompile or redevelop a bunch of stuff because my code doesn't work on ARM64? And then how do I actually practically do it? Like, how do I do deploying and managing, deciding on the fly which hardware platform I'm going to use for a component of my application? And that's where talking about things like multi-arch containers and talking through what we were talking about earlier, Jonny, about how most of the language runtimes work exactly the same. So there's very, very little porting to be done. It's more like a migration. You can hit some issues for sure, but there's very little work to do to get, for example, a Java application. There's no work for the most part, unless you're using some exotic JNI drivers, right? But for a Java application, you can run it without even recompiling it on an ARM64 JVM, and it'll just work the same for 30% less.
Yeah, and that's significant. And like that's on a compute side or on the server side, it's one thing. But like one thing I was thinking about too is like when I was trying to think of like why I was actually looking at Pies before. It's right when Edge was really starting to take off, right? And like we were talking about these like localized workloads and stuff like that, and you're trying to run something, some AI, framework on the edge, right? And that's when like the Jetsons, I think, were starting to get really big because you had like these single small frame computers that were running on ARM that had a GPU attached to them where you could run things, and then you actually have like an MLOps kind of flow to it. So yeah, it's crazy when you think of like right now I've got this giant machine in a rack, and I can either keep that same box with an ARM CPU and some memory or whatever, or I can shrink it down and like because you're minimizing footprint. It goes back to the thing, right? Power, space, and cooling.
Right.
Minimizing your space, minimizing your cooling requirements. All it's more than 30%, but
yeah. And that's one of the use cases we've seen people use Ampere instances in the cloud for, is like, I want to do my software development. I want to use kind of full CI/CD. I want to use GitHub Actions. I want to, make sure I'm running a full battery of tests against this environment that I'm building. But it's going to be embedded eventually, right? It's going to be in a Raspberry Pi. But I'm going to use these ARM server instances to basically emulate my production environment and allow me to use the same hardware platform for deployment, and which is a kind of one of the key tenets of GitOps, right? You want to make sure that you're using the same deployment platform for testing as you are for production.
Yeah, when I think about when we go back to the IoT use case, right? And we had my lab had more than 40 IoT servers in it that we did the testing against. And so the servers were, we did over-the-air upgrades on them, and we did, but like fresh installs. Man, I'm pulling this thing off the DIN rail and bringing it over to my desk, because we mounted them on DIN rails on the side, so they had the maximum amount of airflow around them for cooling, and without having to use the fans and everything else like that. And so, we're bringing them, go grab the thing, unmount it, bring it over, plug it into the set of cables that always lived on my desk, not always attached to something, right? Plug it in, bring in, completely reflash from scratch. We're talking BIOS. We're talking I don't think I could do this now, but I used to be able to do it in my sleep. I used to be able to put all that. I used to be able to reflash the BIOS and reflash the OS on these things, and like 3 different types of them, ARM, x86, like I said, and they all were a little bit different. I used to be able to do that in my sleep. Yeah. Which I had a 1-year-old at the time, so I was doing it in my sleep. I was asleep. Right. Doing that whole thing, and the amount of just hours spent on that. Right. And so
wouldn't
the
it be
BIOS,
nicer for every part of that you can do in a VM, right?
That would have been amazing.
In a cluster on
that would have
ARM
been
hardware,
amazing.
and
it was distributed computing. In fact, we were actually migrating it to Kubernetes when I left that company. Like it was effectively the same, model, the same pattern, the same design pattern, right?
Right.
That would have saved me so much time. The amount of time I spent USB drives and special keys, and here's how to set the BIOS password, and then I just lives in my head only. Sorry, when I leave, you don't know how to get into these anymore. It was. I wish I had worked. I wish that had been my IoT working experience. And not that I didn't have a lot of fun. I did, and I met great people and learned a lot of skills. But it would have been so much nicer.
But it's it's not just for these embedded workloads, right? Like we have a number of companies who are using Ampere instances for cloud scale applications. Uber has migrated a ton of their services to ARM64 instances for cost purposes. So you've got things like message buses and object stores and web servers and databases. So it's not just for kind of specialized embedded workloads, right? It really is a general purpose compute platform that's just, for most people, cheaper.
Yeah.
Which is great.
Yeah, it's been very interesting for me again, and I've been a little bit out of it, so I don't have all the knowledge on these. I used to know this stuff really well. I used to be able to tell you the differences between ARM and x86 and all that other stuff. But then you don't look at it for like 6 years and you don't know anything anymore. I'm Jon Snow again. So,
atrophy is real.
Atrophy is real. The skill atrophy is very real. So but it has been interesting to watch from an industry perspective to see this type go to scale. So let's segue back in. So how are, aside from like you kind of mentioned, you can use Argo and everything to test embedded stuff anywhere, because you can actually do it onto hardware. If we're honest, it's not that impossible. But what else are like, how is this, like, how's the Argo rollouts, like, what are you seeing?
Sure. Well, I mean, where Argo Rollouts fits in is, like I said, you've got, because it's a different architecture, you need to make sure that you've got ARM64 containers, assuming containers, even though Kubernetes manages all sorts of compute footprints now. But so if we're talking about a container application, you need to make sure that the underlying container runtime is compiled for the architecture, right? Which is a bit of work. Luckily, Kubernetes has something called, or I should say, containers, OCI containers has something called manifests. Are you all familiar with container manifests?
Yeah.
Okay, that's probably a silly question, but
no.
It was one of those things where I laughed, but then I was like, I value that you made sure and double asked the question so much, because the answer is Jonny and I are. But frankly, you never really know about the viewers. So if you want to go ahead and summarize it, I love making sure that we always start assuming no knowledge so that every episode is good for every viewer. Okay,
well then let me give the 20,000 foot view, which is that containers have to match the underlying hardware they're going to run on, right? They're binaries. They run on CPU hardware. So you've got x86 containers, you've got ARM64 containers, you've got PowerPC containers, and so on and so on and so on. But if you are pulling a container from Quay or a Docker Hub, right, you want to make sure that you can pull a generic container name, like I'm getting Nginx latest. And you want to make sure that you're getting Nginx latest for your architecture. And you want somebody else to take care of that. So what you do in a container manifest is you basically have, it's a list of container images with some metadata and a SHA key linking to an actual image, right? So you pull the manifest says, oh, I'm running on ARM64. I need to get the ARM64 container, and it goes off and it gets the ARM64 container for you, which can cause confusion sometimes, because if you do like, if you call the manifest by its SHA key, right? If you do a Podman pull or a Docker pull with a SHA key for a manifest, the container that actually ends up running has a different SHA key than the one you pulled. And I don't know if that confuses other people, but I've had one or two people tell me that was confusing to them. Because what you're getting is you're getting the binary. It's a kind of a pointer, right? It's a redirection. So you can actually, I mean, most open source projects now generate multi-architecture containers, right? They generate the manifest as part of their build process. So when I go Docker pull Nginx, if I'm running this on an ARM64 node, I'm going to get the ARM64 container automatically. I don't have to do anything for it. So that's the first thing, is you need to make sure that your containers are built multi-architecture. So you're building your container on every architecture you want to support and then generating a manifest from those containers. So that's the first step. The second step is where Argo fits in, is Kubernetes workload placement rules, right? That there are basically three ways that you can do workload placement in Kubernetes. One is with taints and tolerations. So you taint nodes and you create tolerations for workloads where you say, this workload will work on nodes with this taint And then so taints and tolerations are kind of connected. You can use something called node selector. So you can select nodes with a specific metadata, like, disk type SSD, or, this is a node that has a GPU connected or whatever, right? And you can use something called affinities, right? Node affinities, where you say, this application, I'm going to use this type of node when these conditions are met, and I can fall back to something else, perhaps, right? So this is I have a couple of slides on this if you want to share. So okay, so one of the way Kubernetes works with rolling updates is when you do a deployment, it creates a new replica set, and it'll progressively add pods to your new replica set and shut down the pods in your old replica set as that's happening. You've got two parameters that control that. Max surge is how many extra pods you can create before the pods in the old replica set get shut down. Max unavailable is the lowest number of pods that you can have before you stop trying to shut down old pods. And this is workload placement with a node selector. So there's lots of different types of labels that you can put on nodes. You can use disk type SSD. You can use like I said, GPU availability or whatever. And then taints and tolerations, you have a number of additional qualifiers. So some of these get added automatically by Kubernetes. When there's a node that's under a lot of memory pressure, that will prevent new pods from being scheduled on there. Same deal with disk or PID pressure. So taints can prevent new workloads from being scheduled. It can force eviction of workloads to other nodes. So that's a really nice option for those things. And you can combine those with, you can combine those with node affinities. So this, for example, on the right here, we've got basically this pod, or this, I think it's a deployment, but has this spec affinity section, which basically says, oh, this pod or this deployment can deploy to any of these architectures. It can deploy to ARM64. It can deploy to AMD64. You can actually specify, which is preferred or which is required, and it can apply to both scheduling and eviction. And so how this fits into Argo CD is you basically can tell Argo, hey, I want to use a rollout, and I'm going to use a deployment strategy. I'm just skipping ahead here, so maybe I should have done this before. I'm going to use a deployment strategy like Canary or progressive delivery to basically say, okay, what I'm going to do is I'm going to start with all of my application infrastructure working on x86. And I'm going to try and deploy the same container onto ARM64. And I'm going to put 10% of my traffic on there. And I'm going to have some checkpoint where I'm going to have a qualifying test, right? Where you test whether the 10% is working to expectations. So you can have, this is basically using rollouts with something like Canary is a really easy way to basically say, I'm going to have confidence when this thing is running on this new architecture that it's running to my expectations, right? I can test whether it's meeting my KPIs. I can test whether there are issues and fix them progressively without endangering my application. So yeah, this is really one of the ways I suggest doing it. So this is before. We can actually stop the slides. I think yeah. Let's stop the slides.
No problem. I was gonna say the real value for that is finding the unknown unknowns, right?
Yes.
I think we always know, doesn't matter how good our testing is, the goal of testing is to know what bugs you have going into production, not to go into production without bugs.
Right.
That second thing is as impossible as a 100% service level objective, right? You're not going to be successful. There's going to be a race condition or something. Because there are differences in that underlying hardware architecture, and these abstractions are not as perfect as we sometimes pretend. Your hardware does actually matter. The performance of the hardware will actually impact things. I think 99% of people probably, like you said, not going to see something where ARM versus x86 really seems to matter. I'm going to use the example of Slack, right? I have a x86 architecture laptop and I have an ARM 64 architecture laptop, and Slack behaves the same on both of these. I don't notice any differences. Or you could say Slack misbehaves the same on both of these, perhaps. Depending on how you're feeling about it that day. So that's not really going to make a difference.
Right.
I could imagine that there may be some use cases of, maybe extremely high fidelity data streams, where any sort of slowdown or blip in the CPU or whatever, or a change in the way that things are like bin packed and bucketized could alter behavior, where you're highly sensitive to deviations in these bits and bytes. It is so uncommon, I would say, that it's good to always use the best practices surrounding it. But I do think that especially in cloud computing, most of us are not going to be doing things where you would really notice, with the caveat of, I wonder how much the OpenShift team notices, because OpenShift does, there's x86 OpenShift and ARM 64 OpenShift. We actually have a few things in there. I don't know if you've ever got a look. There's a few. For Arrow specifically, we when we're creating the new OpenShift install targets in our service, we make sure to make that the ARM and the x86 images were all where they ought to be and everything like that. So right. I've had some fun going in and making sure those things are taken care of, and just always validate the process, validate that things are where you expect them to be and how you expect them to be there. So for us though, everything just works. You know what I mean? Like we do the stuff that we add to an OpenShift cluster to make it the managed service. We do nothing special. We make sure to have the images that are ARM images or x86 images, or as appropriate, so that things will, not have meltdowns. But that is only because of the declarative nature of Kubernetes, not because we have to do something special. It all just does the stuff.
Yeah. And that's going to be a very common. So there is work for like the OpenShift team, right? They have to make sure that they're building all of the OpenShift artifacts for all architectures supported. They need to, and validating that on all architectures, and validating, various things like migration behavior, right? Do the right things happen that are supposed to happen? But yeah, for end users, really the experience should be transparent. If you have your application in multi-architecture containers with a manifest, and if it's been tested on all the platforms that you want to support, as well as I do, that Argo doesn't really have any concept of the architecture for workload placement. You're just basically saying start this thing on this node. And once the thing can start on the node, then it will start on the node. So what's really interesting for me is that, like, Argo provides some of those capabilities with rollouts to say, okay, I'm going to surge to 10%, and I'm going to have a stop, and I'm going to run a test suite, and I'm going to surge to 20%, and I'm going to have a stop, and I'm going to wait for user validation that I can now go to 100% or whatever. And that kind of like encapsulating some of those best practices of GitOps and of continuous delivery really make it, in my mind, really easy to have an architecture migration with confidence. And that's what this is going back to what you were saying. Is it's not about zero bugs, or zero bugs, as Bugzilla used to put it. But it's about having confidence that you're discovering what you don't know.
Yeah.
Yeah, Argo Rollouts is an awesome tool as well, because like
It is
with what you showed specifically, the blue green, like just configuring blue green and just setting that up to where you can actually do this migration. It's pretty damn painless. I mean,
Yeah,
it's
and I didn't
super easy.
I didn't show like the Argo Rollouts command line tool. You can use
Mhm.
Argo Rollouts without using Argo CD at all.
Yeah.
Yeah.
But obviously, I recommend using Argo CD because continuous delivery is awesome, and it's really the way you should do cloud applications. And then the rollout CRD is really it is spectacular. It's awesome, and I have to call out the documentation on the Argo website for Argo Rollouts is great. And I have to call out in particular like Michael Crenshaw and the folks at Intuit who developed and use this a lot are the people who kind of got me onto this in the first time, and I really see the value of this for people who are using.
Yeah, Argo Rollouts is amazing, and for those that don't know what he's talking about from the CLIs, you can actually, it's a plugin, right? So that you can use it alongside your kubectl and OC and all that stuff. If you're using OpenShift GitOps, then it's built in. I think since like OpenShift GitOps 1.14 or 1.13 or something like that. I'm not even sure.
It's been a minute, yeah.
It's been out there. It's actually it's pretty amazing. If you've ever done like any real canary testing or anything like that, like back in the day, canary testing, like it's kind of tough. And then even doing like the blue green stuff, like it's simple enough in concept to do, but like actually putting it together, it's kind of a pain. But
and you can do it manually with deployments, right? It's not impossible. I mean, that's what Argo uses under the covers, as far as I know. But having kind of like really the most common patterns for deployments, blue green, canary, progressive delivery, and I know I'm missing 2 or 3. Like just having those encapsulated in all of the metadata that you might have around how you want to do that and how you want to do test phases or gating phases.
Yeah.
It's just really powerful.
Yeah.
And super useful.
I think Christian at one point 100 years ago was doing something with like Argo Rollouts and Prometheus. So like that's the inline testing that you're talking about, where you hit like your threshold, your 10% or 15% or whatever, and then it scrapes Prometheus for the metrics off of like the application to really like measure the health of it, right? Is this thing doing what I'm thinking it's doing?
Right.
Are people clicking the button I think that they're clicking, that type of thing, and then taking that feedback and then either moving to the next stage or rolling it back completely and saying, hey,
and you can custom define health probes, right? You can have health probes that are based on functionality, based on, because out of the box, I think it's like it'll check whether the containers are running, right? And if the containers are all running, then it says, okay, we've met the threshold. But you can have custom health probes that basically test whatever you want. You can test. You can make sure that ping time is not lower than a certain amount, or that your response time for your P99 latency is not lower than. You can basically do whatever you want as long as you have a script that can measure what you care about.
Yeah,
I think it's so interesting. So, way back when, blue green tended to refer specifically to. We talked about this forever ago on the stream back when it was Christian and I. Blue green used to be a way of evaluating changes and whether or not they negatively impacted conversions. So, for example, if you have a new UI change you're thinking about doing for a like an e-commerce, which was a lot of my original experience for like an e-commerce website, right? And the blue green would be, it's really just 50-50, right? That's really all it means is 50% is this, 50% is that. It was not about finding bugs. It was about validating the business value of the change.
Okay.
And it's interesting. This is, again, we're going back more than 10 years here.
I would have thought that would be like canary builds rather than. So I've always seen blue green as the blue is the one that's out front and green is the one you're building in the back, and then you sort of swap them around. That you've got a private version and a public version.
Yeah, and so you would do it with feature flags. So what we would do is like one of the ways that we would do it is we would do there were a few methods of doing this, but this goes back to like how old feature flags are.
Right.
You could do feature flags against so like in a database against like specific accounts, and then enable the feature flag for those accounts, and then those accounts would get the new UI, and the other non-feature flag enabled accounts would get the old UI, and then you could do a global enablement of the feature flag, and then ultimately the final version of the migration was to remove the feature flag by changing all the backend stuff so that the original blue no longer existed and what was green is now considered blue. That was like one of the patterns for doing it. I always think it's interesting because the way again, a lot of that was about business logic and validating conversions and engagement and so on, not health. But as we've moved to declarative computing, you can do the same thing and validate health. So every time I hear blue-green, I kind of like giggle because it can still be used that way. There's no reason to not use it to validate conversions, any of these processes to validate conversions. It's just that the reason for doing that used to be more about business value, at least as far as like how I saw it in the industry at the time. And oh man, the pains we went through to set that stuff up. Like I mentioned, all these database flags specifically set to accounts and sessions and all this other stuff. Oof. Glad we're not doing that anymore. It was horrible. I'm sure somebody's still doing it probably.
We just created other namespaces. Did everything that way.
Done. Boom.
Ingress.
Right? That's what I'm saying. Just boom, done, easy. Just switch it on the load balancer, no problem.
Speaking of the load balancer, that's one of the things I really like about rollouts as well, is that you don't have to you don't have to configure your ingress to manage where the traffic is going.
I know.
Argo does that for you, right? So ingress, not having to care about the ingress and the services is really, really pleasant.
Yeah.
It's such a thing of beauty. And just being able to do that with some lines of YAML, right?
Yep.
It's so, that's why we like GitOps. It's so declarative. It's all of these things. Like I talked about, what did I just walk us through? I walked us through database schema changes, right? To add the field for the feature flag. Database updates to set a value for the feature flag, right? Server and software upgrades, right? That had to be done first time I did it was actually just straight up on the hardware. Second time I did it, it was VM pools. Right? Like all of these things, all of the levels of like work and orchestration we had to do for that. And now it's have Argo CD and a few lines of YAML and boom. It took 4 people to do all those things. And you can now you can do it with an open source tool and a few lines of YAML is code, sure, but like not even like code. It's configuration.
Yeah. It's metadata.
I love it so much. I cannot. And sometimes I talk to people, and I'm not that old. I just didn't go to college, so I got a head start. Sometimes I talk to people who didn't live through those days. They weren't at tiny startups doing things in strange ways back in the day. And I'm like, we spoiled you all. You all have no idea how spoiled you are because we hated this so much that we fixed it.
And
now
the
they
cool
have
thing,
Argo CD.
Exactly. And the cool thing about rollouts too is, like, especially on the Canary side, right? You say I want 10% or 15% or whatever it is, right? Whatever distribution that you want to go to your new site. That's typically a service mesh, right? Where you're mapping out your traffic. You're really kind of controlling that traffic flow into that particular application and stuff like that.
Yep.
And you get all that insight back, and it's free. It's not free, but it's freer than service mesh, right? Because service mesh is very resource intensive and stuff like that. So it's like you get a lot of value out of it.
You're still using like whatever ingress controller you're using might be a server. Like you might be using Istio as your ingress.
That's true.
Right?
Yeah.
Or you might be using Nginx, but it's like Nginx is kind of the simplest load balancing. But yeah, you could be using a service mesh there as well, right? It all depends on what you're depending on for your Kubernetes infrastructure.
Taking me back, the first time I configured Nginx was so pleasant compared to Apache at the time.
Yeah, it is.
Oh man, it was so pleasant, and it's still pleasant. I love seeing Nginx is still, just in containers and everything now. But I like the lack of awareness you need, right? One of the first times I configured Nginx was for a take-home code test for a job interview, where I had to accomplish a thing, and so in addition to building the little app to do the things, the web app to do the things, I actually did all of the Nginx configuration, put it on a DigitalOcean droplet, and hosted it so that people could interact with it instead of building it locally. Although I also made a make file so it would automatically build locally for them. Sometimes I wonder why I didn't get that job. Anyway, I think it's because all of my infrastructure pieces were like really solid and the code itself was kind of like fine. And then no surprise, now I do more of the infrastructure SRE side of things. So that really was probably the key there. But anyway, so I had to do all that. And I remember because at the time, Nginx was like much newer than Apache. And I'd worked with Apache the most. And I set up Apache before. And I was like, I don't want to do this. And my husband, who's also in software and software engineering, was like, oh, just do it with Nginx. And I was like, what? And he's like, yeah. And he's just shot me the link over, I don't know, couple of hours maybe. It was so fast.
Yeah, and it's powerful.
Was so fast. It was great. Oh, this takes me back. Cool. Well, I learned a lot today about ARM that I didn't quite know. Some of it I had not paid attention to in a long time or seen, and we are coming up on time. So Dave, any closing thoughts for us? Any things that we should be looking out for on ARM and Ampere in the future?
Well, there is one thing that I've kind of, it's top of mind, is one of the differences between ARM and x86 that I didn't mention. x86 has, so do you know what a kernel memory page is? Like
yes.
Yes. Okay. So on x86, kernel memory page granules are 4K. They have to be. Mm-hmm. They're hard coded, like it's a fixed page size. But ARM allows multiple page sizes. You can have 4K pages, 16K pages, or 64K pages. And the bigger pages are really, really useful for a family of workloads, right? Anything that's memory intensive, that's using large contiguous chunks of memory. You increase your cache hits, you reduce your TLB thrash by having larger memory pages. It's a little bit less efficient in memory usage because you're allocating bigger chunks. But for cloud workloads that are memory intensive, it really gives you like typically a 5 to 10% speed up. And one of the things I would have regretted if I hadn't mentioned it as one of the key differentiators between the architectures.
Do you think
and of course that's the power for the AI and the ML because everything is done in memory, right?
Yeah. So that is my closing thought. I'll leave you with that. And
I have
thank you very much for allowing me to
follow-up question. I have a follow-up question. How does that so network jumbo frames, are you familiar?
No.
Okay, never mind then. I'll go do my own research. Now my question is, how does x86 work with network jumbo frames, which can be really large byte sizes, like up to 9,000 bytes?
Okay. Well, I imagine it would involve the allocation of multiple memory pages, right?
Multiple memory pages versus with an ARM architecture, they could probably do it with one memory page.
Yeah.
Oh, and I know, so large MTU, maximum transmission MTU or maximum transition unit is what MTU stands for. I think it's typically
1,500.
1,500, thank you. Yeah, typically about 1,500. I think the 9,000 MTU use cases that we are seeing are all specific to AI and ML as well.
Okay. That's
something to further be professionally inquisitive about as we go on, Jonny.
Right.
Yeah, and that gets interesting, especially when you start talking about VPNs and stuff like that, because then it reduces, you have an overhead, right?
Yeah, you have the overhead. You have to leave the buffer.
Yeah.
And you can't have mixed network architecture either. So that's hugely different because if you need to have a large jumbo frame, every single computer or node, if you're looking at Kubernetes, but it actually doesn't matter. Every single piece of hardware, computer being smart switches as well, like literally all of it, full stack, must be capable and configured for the jumbo frame. Or what will happen is things will crash. You can get I looked into it. You can get kernel panics and stuff. It is that is bad news. It's bad news bears. Is that the saying? Trying to work on not swearing, Jonny. And I'm not good at whatever the alternatives are. But yeah, it's not friendly. It's a very bad experience. I think you just end up with like a memory overflow and then ooms. And I use out of memory. I call it like it's a verb. I'll say, oh, this thing is ooming. Apparently, yep. I'm the person who did that, and you're welcome.
You're an oomer.
I'm an oomer.
So yeah, not zoomers
right in the heart.
Zoomers, you're an oomer right in the middle. Well, thank you both for having me today. It's been a pleasure to be here. And yeah, if anybody here is interested, have a look at the ARM64 instances on your cloud of preference. And if you're on Azure DPS v5 instances or EPS v5 instances, or the Ampere powered instances, give them a go. Tell me what you think.
Yeah,
awesome.
Very fun. Well, thank you again for coming on. I learned things today and have new things to be inquisitive about. For everybody else, I won't see you in 2 weeks. I will see you in 8 weeks, something like that. I'll post when I'm back. It'll be the calendar will be updated. We'll figure it out. Please just keep an eye out on
good
LinkedIn
luck and enjoy your recuperation. Study your Bonetti's defense.
Yes. Exactly. Thank you very much. Much appreciated. I'll see you all on the other side.
All right. See ya.